Hi, so I want to take a few minutes to talk about the results of that pendulum lab you did. So first thing I want to do is just touch on the shape of the graphs. So people made 3 graphs. The first one was a period versus mass graph, which if you had show origin turned on, comes out to something close to a horizontal line. So that tells us that no matter what mass you used, you got about the same period, which means that there is no relationship. So the mass does not affect the period of a pendulum. And that fits with what we saw in the last module, where if you think in terms of energy, the kinetic energy at the base of the pendulum's motion should equal the gravitational potential when the pendulum is at the highest points. And if you do the UG equals kinetic energy, the mass ends up canceling out. So we don't expect the mass to have an impact on the period. You also made a graph of period versus angle, which again comes out to be a horizontal line, or at least something close to it. Again, it's very, very common that just due to uncertainty in measurement, there's at least a little bit of variation in the period, so it's probably not exactly the same, but it should be close. So there's also no relationship between period and angle. And so the variable that matters is period and length. Now, with the range of lengths that you had available, it's fairly common to get a graph that looks pretty linear. But we have to think a little bit about the intercept. So you saw that as the length got smaller, the period also got smaller. So if we think about a length of 0, we don't expect some positive measurable period when you have a 0 length. A pendulum with no length can't swing back and forth. You need at least some length. So that tells us there should be an intercept of 0. So if you imagine forcing your data to have a point at 0, 0, then going up to match your data, we start to get something that looks a lot like a square root. And so when you linearize, if you do a graph of period versus square root of the length, then you should get a nice linear graph with an intercept near 0, which tells us that period is related to the square root of the length. Now your slope is going to end up with some weird units because we have a rise of seconds and a run with units of square root of meters. So I want to think a little bit about those units and use those to try to get us a step closer to the actual equation. So when we have period is related to the square root of length, that means period is equal to whatever our slope is times the length. And that slope, again, has units of seconds over square root of meters. Now, one thing that it would make sense for the period of a pendulum to be related to is gravity. We have, or rather the strength of the gravitational field. We have that lowercase g showing up in gravitational potential energy, and it doesn't cancel out because it doesn't impact kinetic energy directly. And so it might make sense for G to show up somewhere. Now, if I imagine inside of this square root, if I have square root of L over G, G has units of meters per second squared. If I do 1 over that and take the square root of that, I end up with units of seconds over the square root of meters, which tells us that our units work out if we have square root of L over G. But the numbers don't work out, because depending on the units you used to measure the length, the slope should either be in the neighborhood of 2 seconds per square root meter, or if you used centimeters for the length, it comes out to be 0.2 seconds over square root of centimeters, which is not equal to 1 over the square root of G. So we have one more term in here, and that turns out to be a 2 pi. If you have a number that's just a little bit over 6 divided by the square root of 10, you get 2. So the formula for the period of a pendulum turns out to be 2 pi times the square root of L over G, where G is that number that we've been using this year and is about 10 meters per second squared. Sometimes we've used newtons per kilogram, sometimes we've used meters per second squared. When we're thinking about the period of a pendulum, those units of meters per second squared make more sense. So this right here is the payoff of that lab you did, and is what you're going to need to use to do the problems that are coming up next.